Hello, this is Christy Patton-Lukes, and this video lesson is going to be on equations of state. We've been looking at Jacobian transforms, and we're now going to look at some of the equations of state that might be used to correlate this information. So our goal is that by the end of this lecture, you'll be able to identify the types of equations of state that we use to relate pressure, volume, and temperature data. An equation of state in this sense is a relationship that allows one to calculate thermodynamic properties for the state of a substance, and the most common ones relate pressure, volume, and temperature. Frequently, these are going to be written in terms of the dimensionless group Z, which is known as the compressibility factor, and Z is defined as PV over RT. Now, the best known equation of state is the ideal gas law, which we usually write as PV equals RT, or P total volume equals number of moles times RT. But in this case, what we see is that this is just simply another way of writing Z equals 1. Let's look at the classifications of the most common equations of state. The first of these is the virial equation. The virial equation is simply an infinite series in specific volume, or the reciprocal of specific volume. The next category is going to be the empirical equations. Now, there are many possible empirical equations. The best one of these is the Benedict-Webb-Rubin equation, which was developed in 1940 and has 8 arbitrary constants. Notice that in the Benedict-Webb-Rubin equation, it takes on a general form of the virial equation, which was based on theory, and the constants of the virial equation were functions of temperature, and so it assigns a relationship for those and then gives this complicated exponential expression to kind of pick up all the other missing pieces in this infinite series. The third category are the cubic equations of state. Now, there are many of these. The first and best known originating family for this was the van der Waals equation, developed in 1873. There are many, many others. The three that people have kind of persistently used have been the Redlich-Kwong, Soave-Redlich-Kwong, and Peng-Robinson. The van der Waals equation is essentially an extension of the ideal gas law. The ideal gas law is, in essence, treating molecules as if they are a single point that in no way interact with other molecules. Each molecule is totally independent of the others. The only thing that happens is that they have collisions with each other, but they are perfectly elastic. Van der Waals equation makes two basic corrections. It first says that no, those molecules do take up space, and hence you have, instead of RT over V, you have RT over V minus B. The second correction it makes is it says that no, molecules are attracted to each other, and that's going to vary from material to material, and so we have this correction minus A over V squared that deals with the attraction between molecules. The Redlich-Kwong improvement to the van der Waals equation changes really this attractive term, and it says that, well, this is going to vary with temperature. As the temperature changes, the amount of attraction will change, and also that this is going to somehow be related to the size of the molecule, so you see the B showing up in that term also. The Soave addition to the Redlich-Kwong equation looks like it's a very minor change. It basically is that there is an alpha and an A, both are functions of temperature, and that gives more complexity to the types of molecules that the system can model, the equation can model. And finally, the Peng-Robinson equation is quite similar in concept to the Redlich-Kwong equation. It has a different attractive function of temperature in the numerator, and it has a more complex analysis of how size and shape of the molecule affect that attractive term. Next, we look at corresponding states. That's our fourth category. And corresponding states is a matter of making observations over time that say that certain variables are going to be very closely connected to each other from one molecule type to another. In essence, corresponding states looks at moving the critical point for all molecules so that they fall at the same location and stretching and squishing their data so that they all fall on top of each other. And based on this, they define variables reduced temperature, T sub r, which is the actual temperature divided by the critical temperature, and P sub r, the reduced pressure, which is pressure divided by critical pressure. Now, both of these must be absolute temperature, absolute pressure. Let's look a little bit more closely at the virial equation of state. This one is based on statistical mechanics theory. The constants B, C, D in this infinite series are functions of temperature. Finally, the most important thing you need to know is that, frankly, these constants are not well understood or well known. For most fluids, all we're going to have is B of T data. And as a result, we're going to use a simplified form of this equation where we say Z is approximately equal to 1 over B, which is a function of temperature, divided by the specific volume. Next, let's look at the van der Waals equation. Now, it's P equals RT over V minus B minus A over V squared. And for an ideal gas, which I will abbreviate just with an IG, what we have is that this is valid whenever A and B are both equal to 0. Now, this was the first cubic equation of state, and it may not look cubic right now, but if we rearrange this so that we multiply through by all of the denominators, V minus B and V squared, and pull together groupings of Z's, we see that we get a cubic equation in Z. So it's Z cubed plus a constant times Z squared, a different constant times Z plus a third constant, and that would be equal to 0. Now, these constants relate to the original form as A is equal to the negative of PB over RT plus 1, capital B is AP over R squared T squared, and C is negative AB P squared over R squared T cubed. We can find values for these, which are fixed values for a particular material, by using definitions of how a critical point works. Now, we'll be discussing this in a future lesson, but basically we're going to be looking at how pressure volume changes happen at an isotherm as we approach the critical point. So we're going to look at dP dV at a value of T equal Tc and the second derivative of P with respect to V along that same isotherm, and these will both be 0 at the critical point. Therefore, we can use these to solve for A, B, and C. Working with the original form P equals RT over V minus B minus A over V squared, we get that lowercase a is 27R squared Tc squared over 64 Pc, and B is RTc over 8 Pc. If you substitute these values in, you can get capital A, capital B, and capital C, and you can solve this uniquely for Z, and it turns out that the critical value of Z is 3/8. The general cubic equation of state was rewritten by Smith, Van Ness, and Abbott into this form you see here at the top. So P equals RT over V minus B minus an A that's a function of temperature over V plus epsilon B times V plus sigma B. And then if you do that, you're going to get some sort of general forms. Now, some of these are going to require us to introduce the Pitzer eccentric factor, omega, which is -1 minus the log base 10 of the vapor pressure in reduced variables evaluated at a reduced temperature of 0.7 or 70% of the critical pressure. If you do this, you see that you get common definitions here. So van der Waals, A is 1, Redlich-Kwong, it's TR to the -1/2, and for SRK and PR, Suave, Redlich-Kwong, and Pang-Robinson, we get much more complex things that are written at the bottom of the screen. Sigma for the Redlich-Kwong family is 1 and epsilon 0, but for Pang-Robinson it's 1 plus square root of 2, 1 minus square root of 2. Notice the critical Z value that we get. You get a little bit of a difference. So for van der Waals, you're going to get a critical Z value of 3/8. Redlich-Kwong family gets 1/3, and Pang-Robinson gets 0.3074. So this number is sort of fluctuating in the vicinity of the van der Waals. Now, this is a cubic equation of state. If you were to rearrange this, you could get it into that form somewhat like we looked at moments ago, z cubed plus a constant z squared, etc. And if you graph these, what you're going to see is that just like you would expect for a third order polynomial, you're going to sometimes have something where there are 3 roots. So you take a line across here, 3 roots. And sometimes you're going to get a system where there's 1 repeated root, and sometimes you'll have something where the root is out in the non-physical land. We are going to really struggle mentally with what it means to have 3 roots. We know that physically that's not possible. And for a pure system, we know that we're going to end up with only 2 phases. And so if it is a liquid-vapor mixture, we're going to have a liquid and a vapor answer that should come out of this. But we're going to get 3 answers. So we will be needing to deal with this also in a future lesson. And finally, let's look at the theorem of corresponding states. So this theory says that all fluids, when compared at the same reduced temperature, remember that's T over Tc, and reduced pressure, that would be P over Pc, have approximately the same compressibility factor, Z, and all deviate from ideal gas behavior to about the same degree. So for instance, this diagram here I believe is for methane, and if you look at this, as you change the temperature, we get Z versus P diagrams for different temperatures that change. If you then look at what the corresponding states theory predicts for simple fluids, meaning very round, essentially, we end up with this as our diagram. And visually, I can see that this could be stretched or compressed to get to this same shape. Now, there is data tabulated. Like Lee Kessler are the ones that you want to look for when you're trying to use corresponding states. But Lee Kessler data can analyze based on TR, PR, and you'd like to know omega. You can use that to predict Z, the compressibility factor, but also values for enthalpies and entropies. And again, we'll be looking more at this in future lessons. So this concludes this lesson. Thank you.